Hello, my name is Ben. I'll be giving a presentation on calculating the return on investment for choices of compute architecture when the value of the results from that compute platform are not quantified. I'm going to start out with sort of motivation. I'm going to make the story that you're an application developer and you work in some environment where rapid prototyping is reasonable. And then the question that you're faced once you're done with your rapid prototyping is sort of a triage, right? Should I run this application at scale on maybe the cloud infrastructure, or should I invest heavily in the tailored infrastructure, or maybe a streaming architecture, right? So I face some choices when I want to migrate this new application into a large-scale environment, and the question is, how do I choose which one of those platforms? If you're in a commercial business, the answer is you calculate the total cost of ownership and the ratio of that to the expected return on investment. But so in a commercial case, there's a financial motive to do the right thing. For government and the national labs or scientific computing, you can do the first half of that calculation, which is total cost of ownership. But on the output side, science and the government don't generate revenue, therefore it's harder to do that calculation. So this presentation is focused on how to do this triage analysis for scientific and government computing when there is no revenue being generated. You still can figure out which platform makes the most sense. In this presentation, I'm going to present two different independent numerical models. One is focused on if I have a single analytic and I'm looking at figuring out which platform makes the most sense over the many years. The second model is where I have multiple analytics and existing infrastructure and a decision of what to do in the next fiscal period. So in that first model, again, it's for the single analytic over the lifespan of a few years. And I'm assuming that single analytic is running over and over and over as many times as possible. The first cost model that I have is something where it's like AWS, where you charge an hourly rate and you have very quick startup time where you just launch the instance and it's ready to go. And the time to solution maybe there's 100 minutes. The second cost model is where you buy your own hardware and you host it. There the cost is in terms of capital and O&M, with capital being a one-time $100,000 cost and operations and maintenance being $10,000 per year. So here it takes a little bit more time to get spun up, so this is time to market's a bit longer and the time to solution is a bit faster. Lastly, we have this very expensive option where we tailor the architecture to the application, and there it's very expensive in terms of 10 times more than what we would have paid with just a commodity infrastructure, and also 10 times more than if we had just bought commodity infrastructure. So maybe the system administrators here and programmers are more expensive. The advantage, though, is that with that tailored architecture, it's very, very fast compared to the other two solutions, but on the burden of having a time to market very long due to the design and acquisition of that tailored infrastructure. So these are the three models. The first metric that we can calculate pretty easily is total cost of ownership. This is just the addition of capital plus O&M as a function of time. So here on this axis I show the time of 5 years, and this is the cost spent for that platform. If we zoom in on the region of interest, for that tailored infrastructure we spend $1 million, and then there's no O&M cost in that first year, and once we turn the system on, it starts costing us O&M. For the hourly charged by the hour solution, it's just a linear increase as a function of time. And here in this metric, the clear winner over anything more than a few days, is the commodity self-hosted infrastructure. It's clearly cheaper than the tailored infrastructure, and the hourly rate just loses because you're just paying all the time. So the next metrics are time to market and time to solution, and I'm going to point out here that your time to market is about a year, again, for the tailored architecture, but then once you turn it on, the time to solution is very low, so the number of solutions provided blows up, right? It's very fast per calculation, so it's going to generate a lot of answers. The two nuances I'm including in this model is Moore's law. So I'm making the assumption that if you buy a static platform, you buy your own hardware, you get what you have for the next 5 years. Whereas if you stick with a cloud model like Google Compute Engine or AWS, you can benefit from Moore's law in that they're constantly refreshing the hardware under the hood. The other nuance that I've included here is the fact that maybe you have different availability for the different platforms. The external cloud, very reliable, whereas the tailored architecture may be less so. Again, if we zoom in on where the story is, the tailored architecture doesn't produce any solutions in the first year, but then quickly dominates in terms of number of solutions provided. The external cloud like AWS or Google Compute, the number of solutions provided grows exponentially because it's being sped up in the background. The most important slide from this numerical model is what I call bang for your buck. This is where you have, again, the time of 5 years, and then on this axis the cost per solution provided. So the first calculation that you do on your computer is the most expensive, and then over time, because you're generating more and more solutions, the cost per solution is decreasing. With external cloud like AWS, you're decreasing exponentially, but that doesn't keep up with the fall in the cost per solution compared to the commodity infrastructure. And then the way to benefit from this numerical model is to say, if my analytic is going to run for only a few days, I get the most bang for your buck from running on the external cloud like AWS. And the reason for that is just simply you don't have that big capital investment. But if you have some idea that your analytic is going to run for more than a few days, then it makes sense to invest in the commodity infrastructure, where you pay that upfront cost, but then it's cheaper over time, as long as you don't go for, say, more than a year, given the set of parameters. After a little more than a year, though, if your analytic is going to run for longer, then it makes sense to buy a tailored infrastructure. So you get nothing for that first year, but then over time, it pays for itself because it produces more solutions. So there's more cost of that system, but because it provides more solutions, it has a lower cost per solution in the long run. So if you knew all the parameters for capital and O&M cost, and you knew the application was just going to run over and over, then which platform depends on the durability of that application. For our second model, this is completely separate from the previous one and answers a very different question. The assumption here is that I have existing infrastructure and I have a whole bunch of different applications running in production. And the question I'm faced with as a manager is, I'm going to spend some money in the next fiscal period. Should I buy more of what I already own, just to augment it with the existing infrastructure? Or should I invest in something new? The reason I would be motivated to invest in something new is, although maybe it's more expensive, it's also faster. So you can see that sort of borne out in these set of parameters where I have an existing infrastructure with, say, maybe 5 racks of compute or 5 compute units, and then that's of architecture A. There's a capital cost that I know for that value of the architecture is $20 to buy architecture A, and there's an O&M cost associated with that, which is $5. Now, I have another choice. I could also buy something more expensive, architecture B. And again, the O&M cost is correspondingly slightly higher. And the question is, I have $100 to invest in the next fiscal period. Should I buy A or B? Now, what I know about architecture A is that in that 5 compute units, I was running this workload, where the first application took 40 CPU hours, the second application used 100 CPU hours, and so forth for 5 different applications. I've gone and investigated that on architecture B, I get a speed up. It's more expensive, and the benefit is it's faster. So it's only taking 30 CPU hours for the first application, and the second application is 10 times faster than what it is on A. So that's a big benefit. And similarly, all the other applications are faster. So when I run my MATLAB model, I'll switch over to the source code for that. The source code is on GitHub. This is a MATLAB-based numerical model where it's called homo versus hetero. This is the whether I stick with a homogeneous or switch to a heterogeneous environment. And what I'm going to show in the presentation is the output from that numerical model. So when you run the numerical model with the parameters I previously showed you, running the application workload on architecture A takes 31.4 hours. If I buy architecture A, more of it, with that $100, it takes less time, only 19.6 hours. So that's as you expect. You buy more infrastructure, you take less time. Now, if I have that $100 and I ask, should I buy architecture B? Now we're making the environment heterogeneous, and you'd have to figure out for that workload, does it make sense to move everything to B, or does it make sense to only run some of the applications in architecture B? And so I just did a brute force search through all the different permutations of that parameters, that SVET, and it turns out the workload gives the minimum time to solution when one of the applications runs on B and everything else stays on A. So with that configuration of some of the jobs running on A and one of them running on B, the minimum time to solution is 21.4 hours. Because that value is larger than the time where I just had more of A, it makes sense to buy more of A. Now, if I change one value, the capital cost of A, to be slightly more expensive, the consequence of that is that I can buy less of it with that same $100, so the time to solution for sticking with a homogeneous environment is slightly longer than it was where I had the capital cost was lower. So now this value has increased and it's exceeded what we had when we just bought more B. So again, when I bought architecture B, one of the applications ran there and the other application stayed on A, and that time to solution is now lower than if I had just bought A. So therefore, in this case, it makes sense to augment my existing 5 compute units of A with however much I can buy of B. So this is the conclusion of the second model. Again, this was to figure out if I have a commodity infrastructure and I want to know whether to buy a novel architecture, this gives the answer to that question in terms of increasing mission throughput. The model is actually a bit more generic than what I showed. You can have as many platforms included in the input as you want. You can investigate 3 choices, 4 choices, and as long as you know the workload and the speed up or decrease in performance of each of those workloads on the different platforms, you can do a brute force search to find the best throughput.